All right, very good afternoon to all participants who just attend this seminar, and also welcome back to participants who have been joined with us since the first seminar of Class Professor Program. Thank you very much for your great attendance on this program. And today we are very delighted to inform you that we will have four speaker, yeah, who will talk about the progress in polymer and polymer composites technology. And as we spread the informations in our flyer, yeah, we have four speakers for today's seminar. The first speakers will be Prof. Pakor or Prakasi from Dhammasaya University. And secondly, we have Prof. Basuki from North Sumatra University. And thirdly, we have also the speaker, yeah, from BRIN, or National Agency of, I check the affiliation first. Okay. Yeah. Prof. Subiakto from Research Center for Biomaterials, yeah, National Research and Innovations Agency in Bahasa. It stands for BRIN. And also another speaker, also from the same institution, from National Research and Innovation Agency. He is Dr. Muhammad Nasir from Research Unit for Clean Technology. So I do believe today we will have the great setting from our invited speaker, and hopefully we also can have a great discussion, yeah, with all invited speakers today. So again, welcome back, and thank you again for your great attendance on our seminar. As I informed in the previous seminar, so this program fully supported by Ministry of Education, yeah, Culture, and also Research and Technology of Republic Indonesia, yeah, through the LPDP program. And yeah, this seminar also supported by World Class Professor Scheme D for 2021. So thank you so much for your great availability to attend with us. Now we are still waiting, yeah, for the speaker to be joined with us. And I see here from the participant list, yeah, I guess not all from chemistry department UPI, but I guess some, yeah, from other institution, also from Garut University. Thank you so much for your great attendance in our seminar. Yeah. Yeah. Also, selamat siang for national participant here, and I guess I noticed some participant, yeah, from abroad. I guess here there is Mr. Buntonim. Good afternoon, and also Mr. Charni or Mrs. Yeah, and also Pak Jainuddin from BRIN, as well Pak Ismail Budiman from BRIN. Thank you so much for your great availability to attend our seminar, and also some participants from other university, yeah, in Indonesia. Welcome to our seminar. Yeah, it's almost close to 1 p.m. Still, we are looking forward to the how to say attendance of our invited speaker. So for all participants, as we mentioned in our flyer, we will provide e-certificate. Yeah, please kindly fulfill your information by the end of this program. Yeah, soon after the conference or seminar, how to say, completed. Yeah, we will quickly send the e-certificate to your email. Yeah, as usual. Yeah, and hopefully from these activities, not only we can gain the new knowledge and experiences on how to say advancement, yeah, in the polymer research or polymer composite research, but hopefully in the future also we can, connect it each other, yeah, to have more collaborative work in the future. All right. If you have any inquiry or other questions, yeah, please kindly employ your chat box. Yeah, you can even say hi to other participants, just in case maybe some of your friends also attend this seminar. Yeah. And for the questions, you also can drop or put your question in the chat box. Yeah. In the Q&A session, I will read your questions, and even though, I will provide you the opportunity to deliver directly the questions. Yeah, so please stay tuned and also stay in touch with us in this seminar. Yeah, because yeah, we will have a great time. I hope during this seminar. I guess the speakers already joined with us. Selamat siang, Prof. Subiakto. Assalamualaikum.
Waalaikumsalam, Bu. Selamat siang.
Selamat siang, Prof. Thank you so much for your great availability to accept our invitations. Yeah, we are very happy, yeah, to have you here, Prof.
Okay, thank you.
Yeah. The committee, could you please pin Prof. Subiakto and also set him as the co-host to make it easier. Still, we are waiting for other speaker, Prof. Korn as well as Prof. Basuki. Yeah, hopefully there is no any obstacle, yeah, in terms of internet connections or internet streaming. Yeah, since we fully conducted this meeting by online. Yeah. All right. Pak Nasir already joined with us. I guess still in progress. All right. Anyway. Just for your information, here in Bandung City, we have the frequent precipitation, especially in the noon time until night, especially. Yeah, hopefully also we have no problem, yeah, with the internet connections. And I checked Pak Nasir also already joined with us. So please kindly wait. I try to remind another speaker to. All right. So the participant also gradually increase. Yeah, Friday is quite challenging since yeah, most of us, yeah, especially bapak-bapak dan mas-mas, yeah, we have the Friday prayer. Yeah, so sometimes yeah, it quite delay, yeah, to join with the seminar. But anyway, yeah, we can wait. Selamat siang, Pak Nasir.
Selamat siang, Bu Fitri.
Ya, apa kabar Bapak?
Alhamdulillah baik, Bu.
Ya, thank you Pak Nasir ya for kindly accepting our invitations ya to deliver the talk today. And I guess to keep the time online, here we provide some information in our flash slide. Yeah, we provide already the virtual background, just in case you would like to open your video. So please kindly set the virtual background for your setting. And yeah, if you don't have any problem with the internet connections, yeah, it would be very favorable, yeah, if you could also display your video. And later on, maybe we can have the great interactions in the Q&A session. All right, let I check for the last, if Prof. Korn already joined with us. If he's still in progress, maybe we can start the seminar, yeah, from the first speaker, who already present here. All right, everyone. So to keep the time on time, let I try to start this seminar. So very good afternoon to all of you, and Assalamualaikum warahmatullahi wabarakatuh. Again, on behalf of the committee of this World Class Professor Program, first of all, I would like to sincerely gratitude again to all invited speakers who kindly, accepting our invitation to share their best practice, best experiences on development of polymer or polymer composite system in their research work. And also I would like to thank for great attendance to all participants who already joined with us. I guess some of you maybe also have been joined with our previous seminar. Welcome back, and very good afternoon. Very good afternoon, Prof. Akbar. You also been joined with us now. All right.
Good afternoon, Professor Fitri.
Yeah, good afternoon, Prof. How are you, Prof?
I am good, thank you.
Oh,
So
yeah,
just
very
have
well,
a
Prof.
little bit of technical problem getting into this link.
Oh, yeah. Hopefully, now it's okay for the connections?
Yes, everything is fine.
Yeah, very happy to hear that. And Prof. Akbar, I'm very delighted and also pleased to introduce other speaker from BRIN. Here, Professor Subiakto also already joined with us, and also Pak
Good
Nasir.
afternoon.
Yeah.
Hello.
Hello.
And
Nice
also
to meet you.
and also Prof. Basuki. I guess maybe he also in the progress to join with us. Prof. Subiakto and Bapak Dr. Muhammad Nasir comes from BRIN, and another speaker, Prof. Basuki, comes from the North Sumatra University. And today I do believe we will have the great setting and also great discussions with all participants who already attend this meeting. Okay. To keep the time, I would like to start the seminar. And as usual, we have 4 speakers here, and each of you, just for your information, we will provide around 35 minutes, for your presentations. And in the last session, we will have a Q&A, question and answer session with all participants who join with us. And here is our 4th seminar, organized by World Class Professor Program. And again, thank you very much for your great availability, especially to our invited speaker here. And for the introductions, as usual, here I would like to briefly introduce one by one of our speakers. So we start maybe from our first speaker. Here is Prof. Akbar of Prakarsit. Currently he in charge as the head of department of Common and Graduate Studies. Of Sirindorn International Institute of Technology, Thammasat University. He also currently in charge as director of Center of Excellence in Functional Advanced Material Engineering. And here is his following educational background. He obtained the bachelor and master degree, bachelor degree from Chiang Mai University, while the master and also PhD degree he obtained from Penn State University, United States of America, in the specialty of polymer option. And here is the following of his work experiences. Beside the one that just I mentioned before, also he has some, I guess a special role, as the executive board of Material Research Society of Thailand, or MRS Thailand chapter. I guess in Indonesia we call MRSID, Indonesia chapter. I guess almost similar. And also he been as the Deputy Director, for Research and Academic Quality Assurance at the Sirindon International Institute, of Technology of Thammasat University. So he very productive, I guess, currently up to 2021, he been published 78 publications in international reputable journal, as well as the patent, quite significant, around 9 patents. And then here is a following of his current research work, together maybe in his colleges in the research institute. So basically, if we highlight the topic, of this research work, mostly related to the polymer processing, polymer composite processing, and also some characterization. Even also he worked with some natural polymer, or biopolymers. So if you have any how to say further questions, or how to say regarding to his current research work, later on, I guess, to all participants, you can have the how to say the discussion, with him in the Q&A session. All right, without any further ado, Propakor, so your turn is can be started now. Please.
Thank you very much, Professor Fitri, for a very nice introduction. Let me share my slide. Okay. So first of all, good afternoon, distinguished speakers, Professor Subyakto, and also Muhammad Nasi, our also Professor Ismail, right? So, and also thanks again, Professor Fitri, for the introduction, and also for inviting me to the WCP programs, and also for invitation to participate in this series, seminar series. So this is the final one, right? The fourth one. So yes. I will update everyone on another part of the research work at our research center, right? Focusing on responsive polymeric hybrid nanoparticles. Right? So I will start from the idea of fabrications, right? Until some potential application of each example of the material that we develop. And for those who follow our seminar series here, so I have given 3 lectures already, and on various aspects of the work that we have conducted. So, and also I think we have recorded the video from our previous lecture as well. For those who missed some of those, right, you can find the link in YouTube of the university. And I think for those who follow this series, right, you also are familiar with our research center, which is the Center of Excellence in Functional Advanced Materials and Engineering, or in short, we call this FAME. And so at our research center here, we conduct research, right, that complete the loop of development of functional materials, starting from design synthesis, computational analysis, right, fabrications, until finding potential application for them. And for this talk today, I will focus on the this outline. I will start with some general information about application of polymeric micro and nanoparticles, and then give the detail, right, of our work on the use of PLA co-GMA co-polymer, and making them into pH responsive functional particles. And then I will move to another group of materials, which is the thermoresponsive gating porous particles, and also magnetic polymeric nanoparticles, right, which can be used in magnetic hyperthermia application, and also can be used as reusable sorbents and also anti-scalant. And I talk a little bit on our recent work, which has been published recently on Kaitosan Polyimphalite, and also multifunction Maxine titanium oxide composite material, and I'll conclude my work, right? So I think everyone probably are familiar with polymeric micro or nanoparticles already. So because if we make polymer into this form, right, into particles and in this small size, we have various type of technique that we can do, and therefore we can tune or we can vary the structure and properties of the particle that we make. And as a result, these materials can be widely used in many applications, right? So these are only the summary of major field of application that these type of materials are used, like in biomedical applications, in cosmetics, in food application, or some coating, or agricultural applications. And however, in the past, this type of material usually made from non-degradable polymer, right? Polymer that cannot be degraded. And because their size is very small, even though each time we use them in a small amount, but when this go to the water resources, right, this can cause serious problem to the environment, right? So this is regarded as primary source for microplastic problem in the environment. So because of this concern, right, so there are some regulation in some country already that not allow the use of these materials already, right? However, the sustainable solution to this is, instead of using conventional non-degradable polymer, right, if we can make this type of materials from polymer that can be degraded, right, so this problem will be solved. So that leads to one of the example of material that we develop at our research center here. So we develop polylactic acid copolymer, or PLA, and then we make this into copolymer that with GMA that have a double bond right here that can be can react, right, further react with other groups. As a result, this copolymer can be considered as functionalizable copolymer, right? We can do some further modification to the structure of these materials, right? And we also know that this unsaturated group, right, are very unique, right, for cross-linking reaction. So therefore, we can make this into cross-link structure, right, either by photo, by thermal initiator, right, and make them into network copolymer. However, because the main, right, the base of this copolymer come from PLA, which is degradable, so we consider this as degradable network copolymer, and we synthesize this systematically. We can vary the content of each component, we vary the structure, we vary the amount of double bond in the chain, right? And after that, we apply this in the preparation of micro and nanoparticles. Right? We can apply various type of technique to make a particle from this copolymer, right? So I now show two methods that we use here, and which can give us particle with different structure, right? So this is called suspension crosslink technique, and also the other one is phase inversion emulsification. So by using this different technique, we can make this copolymer into nanoparticles with different structure, right? One can give us solid particles, right? And the other technique or PIE here give us hollow structure, right? With void inside and shell are made from this copolymer. And so we also investigate further into the mechanism of these two methods, right? So why can we get, right? Why we can get this different structure, right? So we found out that the role of PVA that we employ as surfactant in this system, and also SDS, right? So these two surfactants play a key role in making this along with solvent evaporation, right? Play a key role in making hollow structure like this, right? So if we fabricate this particle at lower temperature by using photo initiator, and we can get this solid structure without the void inside the particles. So as a result, now we have the technology, right, that we can apply in order to selectively or to precisely design the particle that we have. And we also study the effect of the SDS content, right, in size of average size of the particle, and also the size distribution, how uniform in the size distribution of the particle that we have, and we see that SDS, right, the amount of SDS that we add in, right, play a significant role, right, in reducing the size of the particles, right, from bigger size, right, until smaller one here. Also, we can vary the morphology of these particles, right? So by making them has rough surface like this, or become smoother and smoother here, we can control this morphology by varying the degree of cross-linking, right, of the double bond that we have in the copolymer chain. So with lower degree of cross-linking, the copolymer chain has higher degree of movement, and they can form crystal. And as a result, this crystal structure here show up as a rough surface in the particles. But when we increase the crystallinity, we increase the degree of cross-linking, right? This will inhibit the chain movement or the crystallization of the chain, and this make the morphology of the particle become smoother, right? So then we also know that if the particles have a hollow structure here, they can scatter light very well, especially in the UV region. So this can be applied, right, as nanoparticles, right, for cosmetic, especially sunscreen applications, right? So we measure the transmission spectra of our materials, right, that we mix with sunscreen products, and then look at their transmission performance. We can see the clear difference, right, in the UV region, that our hollow particles here can help improving, right, the blocking of UV light, right? And if we converted this into SPF scale, right, we can see that if we use only the base sunscreen, the SPF is 68, and if we add only about 5% of this nanoparticles into the products, right, we can improve the SPF value here. And also, because of the different morphology of these particles, we also can tell that they have different ability in scrubbing of the face if we apply them as scrub it in cosmetic products. And we also need to ensure that this material is degradable, right? Because otherwise, if they are similar to conventional polymer, they also will cause serious problem to the environment. So if we leave these particles in phosphate buffer solutions and look at their mass loss, which indicate degradability of the materials as a function of time, we can see that at 60 degrees Celsius, only about 20 weeks, almost all of them can completely degrade it. At room temperature, this will take longer time. So, for example, here at 37 degrees Celsius. So that is the first system that I would like to share with everyone. However, we also can further modify the surface of particles that are made from this copolymer, right? Because we know that this copolymer has double bond, right? And we can make them into particles first, and then after that, we can further modify or grafting some functional group on the surface of the particle that are made from this copolymer, right? So in this case, we show the process of grafting polyacrylamide, which is responsive to temperature and also pH as well. So when we are successful in grafting this polyacrylamide on the surface of these particles, so we can also use this particle as responsive materials, right? We can then cast this into film, and we can see that the film that we get from these particles, without grafting of polyacrylamide is quite clear, but with the grafting of polyacrylamide, they become a little bit more opaque, right? And they respond to pH very, very well, right? And also respond to the temperature as well. So this has a high potential, right, for use as a tissue culture template, right, or cell scaffold, or can be used as absorbent, right, that have the function of pH responsive. We also study the mechanism of the grafting reaction here, right, by using two methods, right? So if we make the particles, right, from the copolymer, and then we add polyacrylamide into this system, and then use UVC to do the grafting reaction. So if we do this, two reactions happen at the same time. So the copolymer themselves, right, also cross-link, and also grafting reaction happen at the surface, right? So in contrast, if we do this on a different way, right, if we pre-cross-link these particles, right, by UVC in the first step, and then adding polyacrylamide, right? So we also have similar products, right? But the degree of cross-linking inside here, and also the content of grafted polyacrylamide is different, right? So if we use this route, right, we can have a higher content of acrylamide grafting on the surface, right? So this is probably because of the competing reaction that of the cross-linking and also the grafting reaction that happen at the same time if we do this route of the preparation process. So those are some part of the work that concerned with degradable copolymer based on PLA, right? And also recently we have conducted extensive review on materials, right? Polymer particles that have the function stimuli responsive function, and we published two review papers, one on the advanced drug delivery review, which which is the collaboration work that we conducted with Professor Hamid at the University of Lyon, France, and also another one at Siam Journal, which is the Journal of MRS Thailand. So if you want to look at the information of this, also you can take a look at these two review papers. So in those review papers, one of the most interesting responsive materials that we pay attention to is the materials that can have smart gating behavior. Right? So in this sense of materials, right, we prepare particles, nano or micro particles, which is porous particles, right? So have many pores inside. So as a result of this, we can load active compound, right, inside the particles, right? So how to ensure to have a high encapsulation efficiency, right? We need to have gating mechanism that can be closed or open, right? When we change response, we change the environment of the materials, right? So this type of response, right, that can trigger the close or open mechanism can be many type of stimuli like changing temperature, photoradiation, ultrasound, pH, biomolecules, right? And these are some examples that have been done and reported in the literature, and we also summarize this in the review paper here. These are some examples of mechanisms that can be employed, right, to act, right, in the gating mechanism of this type of materials. We can use nanoparticles, we can use macro molecule that have specific function like calyx arene, for example, or cyclodextrin, right? We can use linear polymer that can respond to pH, to temperature by collapsing or swelling in specific environment, right? We can use polymer, responsive polymer that can cover the whole surface of the particles, right? So these are some examples that have been done and also reported already. And this type of materials, right, has wide applications, right, in various fields, especially in biomedical applications, right, in drug delivery, drug control release, right, especially anti-cancer drug, right, which have some side effect to normal cell, right? So we need to ensure we encapsulate the drug, right, until this drug go to specific cancer site, and then we trigger the release, and then this material can perform their function with minimum damage to normal cell, right? So these are also some examples that are included in the review paper, right? Now, let's talk about one of the specific example of our work, right, on this gating porous particles, right? So we prepare the materials, the porous particle here, right, that have the function of thermoresponsive gating, right? So the material, porous material here is prepared from material that is called Udakit RS100, right, which is cation copolymer, right, that contain this positive charge and also acrylate group. So we can make this into porous particles like this by using common technique. And then we show, right, the performance of this particle by encapsulating drug model. In this case, we use now blue A, right, as a indicator, right, because these have color. And then we use polynipam, right, which is a thermoresponsive polymer, right, as a gating polymer that cover the pore structure of these particles. And because this polynipam, right, is responsive polymer that can collapse or swell, right, when we change the temperature, right? So the temperature here is around 34 degrees Celsius. And so if we lower the temperature, the chain can collapse. So this can close the pore. If we increase the temperature, the polynipam can expand or swell, and this open the pore, and the encapsulated indicator here can be released from the particles. So we prepare these materials by two different, by the same method, but employing two different initiator system. Right? The first one use only thermal initiator APS, right? That can generate free radical here, and the other system we use a mixture of two initiator, and this become redox initiator, APS and TMET here. So by using these two different systems, right, we can see that the polymerization of polynipam at the porous structure, right, are quite different, and this also affect the encapsulation efficiency. Right, by using APS alone, the encapsulation efficiency is around 70%. By using this redox system, right, we can encapsulate close to 100% of the indicator that we use. Right, and after that, right, we measure the encapsulation efficiency. We also test the thermoresponsive behavior of the materials, right, by measuring the amount of the indicator here that are released from the materials, right, at the temperature, right, 33 degrees Celsius as the borderline, right? So we lower the temperature lower than 33 degrees Celsius or higher than 33 degrees Celsius, right, to trigger the close and open mechanism of these materials. And you can see the color here, right, indicate how much of the fluorescent dye here, right, the indicator here that come out from the materials. On top of that, right, not only, right, we look at the normal release behavior of the material, we also characterize the precise control of the close and open mechanism here. So we call this switchable gate properties, right, gating properties. So what we do is we take our materials, right, and then start to lower the temperature to 5 degrees Celsius. Right? By doing this, right, the pore structure will close. Right? We keep all of the fluorescent dyes in the particles. Right? So when we measure the amount of the dye, right, that come out, right, so nothing coming out, so 0%. However, when we start to increase the temperature, right, higher than 33 degrees, so go to 40 degrees Celsius, right, you can see that about 5 minutes, we see a release of the fluorescent dyes to around 12 to 13%, right? So after that, right, we cool this back to 5 degrees Celsius again, right? So as a result, you can see the release stop, right? So because we close the gate, right? So 5 minutes from here to here, we do not see any increase in the fluorescent dye. But if we do the second cycle here by increasing the temperature again, right, we see an increase of around 10 to 15% again. So you can see that we can do this around 4 cycles. Right? We can almost completely release the encapsulated fluorescent dye, right, from the particles. Right? So this show very high potential for drug control release applications. Now move on to another system that we developed, right? So this is called magnetic polymeric nanoparticles, right? So we include magnetic nanoparticles into the particles of polymers, right? And as a result of this, we can change, right, the temperature, right, by inducing the magnetic particles, right, by using the mechanism that is called hyperthermia mechanism. So how do we do this? The storm is coming in Thailand at this moment. You probably hear about the noise. So come back to our work here. We use a copolymer of polystyrene and acrylic acid here as the polymer matrix, right? And then we prepare magnetic nanoparticles, right, into small size, and then stabilize this by oleic acid, right? And then during the formation of polymer particles here, we disperse this small size magnetic nanoparticles into the droplet of the polymeric particles. And as a result, we have polymeric particles here that can disperse very well in water that contain, right, small magnetic nanoparticle inside, right, with very high magnetic content and also very high shape stability, right? So how do we know that, right? So when we measure the content of the magnetic nanoparticle by using TGA here, we can see that the magnetic content in the particle is at least 70%, right? So this can ensure us that the material have very high magnetic properties. And if you look at this TEM picture, right, you can also see very clear, right, the black domain here, right, are from magnetic nanoparticles that are evenly distributed into the polymeric particles. And this shows super paramagnetic properties. Therefore, they can be induced by external magnetic field, right? So we can disperse them in water very well, or we can collect them back by using magnetic field, right? In only about 5 to 10 minutes, right, we can collect all of these particles. They are very stable in water because they have very high zeta potential, right, in negative zeta potential, which come from the carboxylic acid in the structure. So what about the responsive properties, right? So we can, if we apply alternating magnetic field, right, or AMF, right, to this type of material by using induction heating machine, right, we can heat up the magnetic particle inside the polymer particle here to very high temperature, right? And as a result, the heat here is transferred to the polymer and make the whole particles, the temperature of the whole particle increase, right? So only about 1 minute, right, 60 seconds, we can heat the particle here into around 45 degrees Celsius, right? And this is higher than the temperature that is used to destroy tumor cell, right? So as a result of this, the material has very high potential, right, for magnetic hyperthermia application, especially in cancer therapy, right? And after heating to this temperature, right, the structure is still intact, so they have high shape stability. Similar materials, right, here, because they have carboxylate group right here, so they can complex with various type of metal, especially metal ions that have two positive charge, right? For example, calcium here. So if we use this material, right, as absorbent to absorb calcium, so this show very good absorption capacity. And the major advantage of this, right, over normal absorbents is after absorbing all the calcium here, right, we can collect them back, right, by using external magnetic field. And after collecting them, we can regenerate this material, right, by using acid solution. And then we can reapply this. So we can reapply this in at least 4 cycles. We can see that the absorbent capacity doesn't change much, right, during this first 3 or 4 cycles. Right? So this can be used as reusable solvent in environmental applications. On top of that, right, because of this ability to absorb calcium or to stabilize calcium, to disperse calcium and preventing calcium to precipitate in the system, right? This also can be applied as anti-scalant materials, right, to prevent scaling in, especially in water cooling system, right? So we measure the anti-scalant properties of this material in comparison with various commercial anti-scalant that are used in the market, and we can see that the performance are almost the same, right? But with the addition advantage that we can collect them after use, right? So we do not discharge this into the environment, right? So this can also reduce the effect to the environment compared to normal anti-scalant that are available in the market. And we also now working on another type, because this material is made from polystyrene co-acrylic acid, right, which is may not be friendly to the environment. So we want to move forward further to polymer that are from bio base and also can be degraded after use. Right? We have a collaboration with Professor Fitri here, and we developed a system of Kaitosan copolymer that have positive and negative charge in the structure, and we can incorporate this into the magnetic nanoparticles that make similar materials that can perform in the same way, and but which is more friendly to the environment. Right? So this work is also undergoing, and they have high potential for commercial use. Right? And I will talk briefly on another two part of our work that has been recently published, right, in Chemical Engineering Journal here. We make Kaitosan Polyimphalite. Right? Polyimphalite means this Kaitosan, right, contain both positive and negative charge in their structure. Right? So this is very, very useful, right, in many applications. Right? How can we make this copolymer? Right? We start from using normal Kaitosan structure, and then we quaternize, right, by incorporating positive charge into the structure, and we have what we call quaternized Kaitosan. And after that, we do another step, right? Oxidizing OH group in the Kaitosan structure and make this into carboxylic acid group, right? By using a new oxidizing process that we have developed, right? Which use Tempo Plus, right? And that are generated from a halogen-free process, which is friendly to the environment and also very low cost comparing to normal oxidation process that have been used in commercial at this moment. So our material here, right, therefore will have a potential for many applications, right? Like as absorbent or as anti-scalant, right? In water treatment applications. Also, because this have positive and negative charge in the structure, we also can use them as shell material for encapsulating various type of active compound and making them into micro or nanoparticles, right? So this work is also undergoing at this moment as well. And also another one recently just accepted last month is this one. So we developed 2D materials, right? That is based on MXene titanium dioxide composite. And the good thing about this is the MXene based material here, I have very good absorption activity, and the titanium oxide particle that we include into the structure, right, will make this material have the photocatalytic properties. Right? So the idea here is we use this type of materials, right, to absorb various type of active compound that are polluted in the water, for example, antibiotic drugs that are contaminated in water. After absorbing this into the structure of magazine, and then we can use UV light, for example, to activate titanium dioxide and then degrade the drug, right? And then we can regenerate and reuse this type of materials, right? So this will be appear very soon, right, from this journal if you would like to have more detail. So with that, I would like to summarize, right, the work that I share with everyone today, right, in the theme of making nano or micro polymeric particles that have responsive properties, so we can change, we can trigger, right, the release and encapsulation of the particles here by changing the environment, right? And also we incorporate various type of inorganic materials into the structure, especially magnetic nanoparticles, right? So the last thing here, I also would like to thank, right, all the granting agency, right, who support us to make our work possible at our research center, and also the key person who contributed to this work in this field, especially the lady here, Dr. Jariya, a PhD student, Kamon Chanok here, Sivanat here, Professor Paibun right here, and also some other student, right, who master student who also contribute to this work as well, right? So at that, I also thank everyone for your kind attention. Right? So if you have questions, we can discuss this after the three work from other distinguished keynote speaker as well. So thank you very much.
All right, thank you very much, Prof. Pakon, for your wonderful presentations. As always, just to add his summary, today we are very, how to say, fortunate since the Prof. Pakon share with us several, how to say, promising system, yeah, on his current work regarding to the development of micro and nano polymeric particles, yeah. I written here more than 7 systems, yeah, been introduced by Prof. Pakon from his presentation. Not only development on degradable polymer hybrid system, but as well the a kind of stimuli response polymer, yeah, it's very interesting. And also the magnetic polymeric nanoparticle that also can be, how to say, employed as the anti-cancer and also for adsorbent, and even it's really good in terms of the usability. It's very interesting, Prof. And also some other system with the magnetic and biopolymeric system. And the last, yeah, about the how to say, another composite system for photocatalysis. Yeah, it's very interesting regarding to the materials. Yeah, I guess. Yeah,
Yes.
from ensin and titanium oxide. I guess some students also here who attend the seminar also working with catalyze. So for all participants, I do believe you have some curiosity and also questions to Prof. Pakon. So please kindly write down your questions in the chat room, or even though you can directly ask the question in the Q&A session. All right. Before we move to the Q&A, we still have 3 distinguished invited speakers here. So secondly, I would like to move to our second speaker. Selamat siang, Prof. Basuki. Assalamualaikum.
Waalaikumsalam Bu Fitri, selamat siang. Very good afternoon everybody.
Yeah, how are you, Prof?
Yes.
Yeah, hopefully yes. Hopefully you are in a great health, yeah, and doing well in
Yeah, thank you.
Okay. Actually very far away, Prof. Pakon, from Bandung. Yeah, by plane around 2 hours. Yeah. All right. To all participants here, I would like to briefly introduce our second invited speaker, Professor Basuki Wiryo Sentono. He comes from Department of Chemistry, Universitas Sumatera Utara, or North Sumatra University, and he is a professor on physical chemistry and polymer. And the following is his educational background. He obtained a bachelor degree from Universitas Sumatera Utara, and for the master degree in physical chemistry subject, he obtained from Institute Technology Bandung, or ITB, and for the PhD degree, he obtained from Aston University, United Kingdom, yeah, especially in Department of Chemical Engineering and Applied Chemistry. And here is some his recent works, yeah. Yeah, it's very, how to say, attractive since he been as a visiting scholar in some institution here in the University of Girona, in the Groningen University, as well as your previous how to say institution, Aston University. And also he been in charge as the internal research reviewer in Universitas Sumatera Utara, and also the regional manager of internal quality assurance, and also a reviewer board of higher education in Ministry of Education and Culture of Republic Indonesia. He been consistently, how to say, perform in publications here from our record. He even has published around almost 200 publications. Very inspiring, Prof. Very inspiring. And some research interest maybe available here for the committee. Oh, all right. So maybe later on your presentation, Professor Suki, you can introduce more detail about your current work with your colleagues in Universitas Sumatera Utara. And without any more ado, time and place is yours. So please, Professor Suki.
Okay. First of all, Assalamualaikum. Very good afternoon, everybody, especially Prof. Pakwan from Thailand. It is very close actually from Medan, yeah. Okay, first of all, I would like to share my slide before. I'm sorry, maybe with a little technical problem because we have all right, hold on then. Yeah.
Do you need any assistance to display?
No, okay. I'll try to share.
Oh.
Yeah, I'll try to share my presentation. Okay, here we are. Okay. So everybody can see my presentation.
Yes, Prof. It's excellent.
Okay. Thank you then. Okay, that's right then. Okay, thank you. So first of all, I'd like to thank you, Bu Fitri, for inviting me. It's very honorable for me, to join this very great, presentation, especially from Prof. Pakon. Yeah, is that right? Yeah, and he has already, discussed everything in very advanced, very deep. Yeah. But my presentation, there is no much magic in my presentation. It's only very basic actually. This is actually our work in the past 5 years regarding the nanocomposites. Natural-based nanocomposites. Yeah, and only at glance. Yeah, glance is our application. We always share. All right. So here we are. I don't want to discuss in general, but this is my outline, because I know my time only half an hour, 35 minutes, Bu Fitri. Okay,
Yes.
So I would like to skip this one, the first one. This is very general about composite, nanocomposite, and hydrogel, and actually the last 3 parts, actually this is our work in the past 5 years. Not actually, this is work of my students, not only my works. Yeah, our research team and they are from our PhD student and master student in the chemistry department in University Sumatera Utara in Medan. Right. Well, I think I would like to skip this because this is a general thing about the composite and nanoparticle and everything, and this is processing of the nanocomposite in general, yeah. And we already include hydrogel as well in my presentation. So hydrogel, we prepare some hydrogels, and yeah, and biopolymers for application. Okay, so I have to directly to go to my second part. This is actually regarding a cyclic natural rubber. Yeah, cyclic natural rubber. This is actually our product in North Sumatra. This is semi-synthetic actually. Cyclic natural rubber actually synthesized from natural rubber. Yeah, natural rubber. And actually we have a small company in Sumatra. And the product actually, the cyclic rubber, usually being used for coating, and for nowadays actually very good for coating for something like ship painting and to protect corrosion on the metal surface. Yeah. And this is actually and we try to develop the cyclic rubber for various printing binders. We call it binders, printing binders. Yeah. And the main problem actually here that the cyclic natural rubber is very good when we use on a metal surface. Yeah. Because the addition is very good. Yeah. But when we don't have to do it on using for printing for a computer printer, but we try to develop to that area. But the main thing when we use for printing on the plastic on the polymer surface, the adhesion is not very good and very inferior. Yeah. And we try to here to produce what we call it adhesion promoters. Yeah, adhesion promoters to improve the adhesion of the cyclic rubber onto thermoplastic actually for printing, for various thermoplastic product for packaging or for whatever. Yeah. Okay. This is our work from mainly from our student here. Now he's already graduated. He got Dr. Mahendra, yeah, Dr. Mahendra, and we have collaboration as well with Professor Hanafi Ismail of USM in Penang, and then collaboration with this is Associate Professor Alberto Mendes from Girona University in Spain, and also with Professor Valerio Cosin from Italy. Yeah. Okay, and this is the simple thing actually. Yeah. When we blend, this is thermoplastic polypropylene especially with cyclic natural rubber. Cyclic natural rubber is not like rubber. This is actually thermoplastic, yeah, because it's not elastic anymore because only cyclicized. The cyclic degree is about maybe 70%. So only maybe 20-30% left of uncyclicized rubber. Yeah. So this is actually thermoplastic. So we can easily blend it actually using a internal mixer, for example, yeah, in the melt temperature. But when we're blending directly here with polypropylene and cyclic rubber, the blend is not compatible. It's not, because they have different properties. The thermoplastic is very hydrophobic, and then the second rubber is more semi-polar. Okay, so this is actually the main thing, how we to improve the compatibility of this material. So we introduce as well, actually, we use nanocrystalline cellulose. This is we produce from palm oil empty food bunch, with the help of our friend from Girona, we produce them both actually from cyclic nanocrystalline cellulose and as well as nanofiber cellulose, nanofiber. Okay, so we produce what we call it adhesion promoter. Actually, we have already commercially available adhesion promoter. Two types of adhesion promoters: high molecular weight adhesion promoters and low molecular weight adhesion promoters. They mainly actually grafted maleic or acrylic on the polymer. So as we can see here, the chemistry, that this is we have something like maleic groups here, maleic acid groups, also maleic anhydride groups. Actually, we can you can see very easily understandable. This is actually from cellulose fiber. You can interact nicely here, even chemically. So they can produce a very good link between the maleic or maleic acid or acrylic group with the cellulose, with the cellulose molecules. This is the basic thing actually. So as we improve this, we have a very good improve on the mechanical properties. And this is the result we have got. That actually we introduced already a low and high molecular weight promoters. This is based on maleic, as I mentioned before. And as we put polypropylene and the cyclic ultra-rubber blends with the low and high molecular weight, we can see improved tensile strength. And the second thing is reduce optical contact angle. What does it mean? This is actually we measure the surface hydrophilicity of the surface using a contact angle. You know that higher degree of the contact angle is mean that it is more hydrophobic, and if the angle is very small, and this is a hydrophilic nature. Okay, so and then if we add these nanocrystals and also cellulose nanofibers, this can function as a compatibilizer as well. So improve the mechanical properties, tensile strength, longest break, and young modulus, and further reduce optical contact angle of the polypropylene and second rubber blends. It means that if the contact angle is become smaller, so the compatibility is better. Okay, and then this is what we produce actually. We produce the maleic and acrylic based adhesion promoters. This is we produce, and we introduce to the blends with for substitution for the commercial high and low molecular weight adhesion promoters. We have also improved compatibility. But did not reduce optical contact angles. Why? Because we have maybe this is free maleic or acrylic based groups, which is this is very hydrophilic. So the contact angle doesn't change substantially. Okay, and then the next result we have done here actually. This is regarding nanocrystalline cellulose and graphic cellulose for antimicrobial biomaterials. Yeah. Right? Well, this is actually the work from our student as well. This is Dr. Saragi and then Dr. Lubis. And this is actually we collaborating as well with our colleague from, chemistry and from Indonesian, what you call it, LIPI, Indonesian, yes, chemical from, everybody I think know, yeah, Dr. Yeni Meliana and also Dr. This is Amanda Stefani, yeah. We have collaboration here, and this, first of all, yeah, we produce nano crystal cellulose from Abaca banana stem. Yeah. You know that Abaca banana is a kind of banana. This is very wild banana. Sorry, yeah, wild banana, yeah, from Aceh mainly, yeah. And the stem is very strong. So the fiber actually contain a very good cellulose fiber. So it try to produce nanocrystal cellulose from that fiber. Yeah. And the application is actually for produce hydrogels. Yeah. Hydrogel from gelatin and gelatin base and Kaitosan base, especially for cosmetic hydrogel, yeah, from maskers and everything. Okay, and the result here that the nanocrystal cellulose, yeah, produced from Abaca banana, yeah, from Aceh, actually we have very fine fiber and every diameter about 5.2 nanometers, very fine. And we produce also hydrogel here, yeah, from, yeah. So the hydrogel actually based on gelatin and Kaitosan containing 0.5% only of nanocrystal cellulose. Okay. And we use a cross-linker here for methylene bisacrylamide, yeah. And we tested the hydrogel, yeah, based on the swelling test, also degree of cross-linking and thermal properties and crystallinity, morphology, and we do also irritation tests of the hydrogel. Yeah. And from this, we recommended that this is very potential for biomedicals and cosmetic hydrogels. And next one, yeah, try to produce grafted cellulose with antimicrobial compound. So we can produce antimicrobial cellulose, yeah, for various purposes, yeah, for anything, for textile maybe, or for tissue, yeah, which is antimicrobial, yeah. That as we can see that the antimicrobial compound is mainly mainly is based on the 3-methyl ammonium chloride. This is actually this is a antimicrobial compound. Yeah, this is monomer, and if you use directly here on the substrate, for example, on the cellulose base or whatever, it can be easily leach out. Yeah, can be easily washed out. So cannot stand for a long time. And secondly, we can contaminate the media. So we try here to graft it. Yeah, we try to, because we have here we have a monomer here, acryloyl oxy groups, double bond, yeah, double bond. So we try to graft it onto cellulose. Yeah. Of course, this reaction, yeah, yeah. And we also introduce Kaitosan as well to help to promote the grafting reaction. So this is what we call it the DRC. This is durian cellulose. I think cellulose from durian peel. Yeah. Okay, and we from here, and then we can produce some cellulose product, which is grafted with the, we call it the salt is a Sayeta compound. This is antimicrobial compound, yeah, and we tested the antimicrobial activity of this compound, right? Yeah, and then we tested also the contact angles. Yeah, this is the cellulose, pure cellulose. See, the contact angle is very high, which means that this is very hydrophilic. Yeah, and after we graft it with the antimicrobial compound, yeah, the contact angle going down, even zero. This means that, yeah, very compatible. Right? Okay, and this is the result of the antimicrobial, yeah, of the compound we produce here. So with some bacteria, yeah. Okay, so yeah, as a result, yeah, the optimum condition here, although the grafting is not very high, the grafting degree is only about 30%, yeah, 30% grafting degree. Yeah, this is the antimicrobial compound with the cellulose. Yeah, this is a Weyer's ordinary reaction on the band. Yeah, at 80 degrees centigrade. Yeah, but the constant monomer of 50% of the antimicrobial. Yeah, and we can see that the crystalline degree also decrease after reaction. Yeah, but water absorption become higher 3 times. Yeah, 3 times. Maybe because some of the crystallinity decrease and the water absorption become higher. Yeah. And also thermal stability until 240 degrees centigrade to 100. Okay, and then if we add some Kaitosan here, the gravity degree is also not very high, only 20, around 21%. But if we put some Kaitosan here in the grafting reaction, and then the antibacterial activity improving. Yeah, maybe because of the especially with these 3 types of bacteria. Yeah, we know that Kaitosan also function as an antibacterial agent. Okay, all right. Lastly, is that okay, Bu Fitri? My time?
Yeah, around 3 minutes left, bro.
3 minutes.
Yeah.
Okay, this is the last one. I won't take everybody's time so long. This is our immobilization of bioextract using hydrogel. Yeah. Okay. This is the work of our student, Ms. Ibu Batubara, yeah, and Dr. Zul Nazri from Loksmawe. Okay. And the main thing here, that this is agarwood leaf. This is agarwood leaf. We have a lot of cultivation of agarwood, especially in North Sumatra, in Pohorok, close to the Loser, yeah, Loser area. We have a lot of agarwood, and usually they produce the woods, but the leaves, actually, the extract, they contain antimicrobial compounds. Yeah. We have already tested. And we try to immobilize this, yeah, using hydrogels, and also the hydrogel is actually based on the carboxymethyl cellulose from the agarwood woods, from the bronze, yeah, because this is actually the waste, yeah, right? And we introduce also nanocrystal cellulose to improve the kind of properties and immobilization properties of the hydrogels. This is our various testing of the extract, yeah, and we have various compounds compound in the extract here, which is the bioactive compound. Okay, and this is also after immobilization, yeah, in hot water, and then we test it, yeah, and still they have some antibacterial activity with after immobilization. Okay, so here the result here actually the condition, yeah, that we use the hydrogel actually use malic acid and carboxymethyl cellulose, and we use also cross-linker here, cross-linker, and we introduce as well nano crystal cellulose to improve the property of the hydrogel. And here, after slow release, yeah, still some bioactivity here, and about 3 main bioactive compounds here from the agave leaf, yeah, especially different groups, carbonates and cyclic siloxanes, yeah. And okay, I think I'm sorry, I can't explain much more about this bioactive compound. This is actually out of my area. My area is only polymer, yeah, hydrogel, but as yeah, that actually we can use the hydrogel, yeah, and this is actually because the bioactive actually for mainly for wound, yeah, wound healing or whatever, yeah. It's not for edible hydrogel, but this is for, yeah, because the bioactive actually this is an antimicrobial compound, yeah, yeah, you can produce that, and yeah, I think, yeah, that's all. We some glass of our our work regarding the natural based nanocomposite hydrogels. Yeah, and we would like to thank to our, of course, our sponsors. Yeah, and mainly scholarships for our students. Yeah, from Ministry of Education. Yeah. And also, this is actually from Orisa team. This is our previous student, now already graduated, Dr. Mahendra, Dr. This is Saragi, Dr. Lubis, and also Miss Batubara is soon will be graduated, and Dr. Junazri. Okay, thank you very much for your attention.
All
I think
right.
that's all, Bu Fitri.
All right. Thank you very much for Prof. Basuki for your great sharing, yeah, on your current work. This is really, how to say, inspiring, since you utilize several type of how to say natural product, yeah, that available, especially in the North Sumatra. For Papua, just for your information, durian from Sumatra, I guess maybe one of the best, yeah, that we have in our country.
Yeah, but this is natural.
Yeah, I should visit and try that.
Not like Thailand. Thailand is I mean, it's a durian, bigger size and whatever.
Yes.
Yeah. Even he got the great inspiration, yeah, to develop research work based on the natural product. I wrote here not only agarwood, natural rubber, but as well but also the durian peel, yeah, can be used as the, how to say, the starting material, yeah, for preparing the hydrogel composite, and also the biopolymer composite, yeah, for several applications. If I'm not mistaken, even though for antibacterial materials, yeah, that you can fit there. So I do believe, yeah, participant would have some questions, or how to say, inquiries, yeah, due to your presentation. Again, thank you, Prof. Basuki, for your great study.
Okay, thank you very much.
Afternoon, and then
okay.
Sorry, Dr. Fitri, you're still mute.
Yeah. All right, dear all participants. So now we come to the third presentation that would be delivered by Professor Dr. Subiakto from Research Center for Biomaterials, National Research and Innovation Agency, or Indonesia stand for BRID. Yeah, previously it well known as LIPI. Yeah, Lembaga Ilmu Pengetahuan Indonesia. And here is his following educational background. He graduated for a bachelor degree from Institut Pertanian Bogor in Faculty of Forestry, especially for forest product technology. And for master degree, he obtained from University of Melbourne, especially here in the School of Forestry, Faculty of Agriculture, and PhD as well in the same field from Kyoto University, Japan. So I can call Prof. Subiakto as sensei, yeah. All right, and again for his current publications, here we try to summary from his Scopus as well as Google Scholar. He recently has been published around 60 publications, yeah, and very consistent in the field of biopolymer processing, yeah. Some topic here we capture in the slide, yeah, regarding to the investigations on the effect of cold water treatment and hydrothermal carbonization, yeah, of oil palm trunk fiber on compatibility with cement for preparation of cement bonded particle board, yeah, and also some modifications, yeah, of novel bio-based adhesive, yeah, from citric acid and sucrose. Yeah, it's really interesting. And also even he produced sorghum pellet, yeah, for electricity generations in Indonesia. Especially he investigate about the life cycle assessment of this material, and still many more, I guess. Yeah, we will have not enough time to read all. And any other slide? All right. I do believe if all participants have great curiosity to his current work, later on in the Q&A, we can discuss in detail. So, Prof. Subiakto, now time and place is yours, please.
Okay, thank you very much, Bu Fitri. Good afternoon, ladies and gentlemen. Also, I'm very glad to meet Prof. Parkon, also Prof. Basuki, my senior.
Welcome.
So, Dr. Nasir, and also all of the participants. Yes, as two previous presentation is more chemist. My background is more forest product technology or something like that. So a bit different side, yeah. So I would like to share my screen. Okay, so is it okay, Bu Fitri?
Yeah, perfect, Prof. Yeah.
Okay, thank you very much, Bu Fitri. Can I slide show here? Oh no.
Yes, that's excellent.
Is it okay? So
Yeah,
I just,
it's excellent, Prof. Yeah.
okay. So the title is a development of an application of natural polymer based biocomposite. Mainly this work is with my colleagues in the SATREPS program, cooperation between LIPI and Kyoto University. So Dr. Endrawati she is a lecturer in IPP University, and Prof. Umemura is from RIS Kyoto University. So this is the outline of my talk, a brief introduction of the potential of natural fibers in Indonesia. I will go quickly on this. And this is the application of the natural fiber for composite. I'll introduce three product: particle board, molding product, and PLA wild warm fibers composite. And summary. I think Dr. Adli Lubis last month already mentioned here. So this is our complex of office, about 50 kilometers south of Jakarta, and the area is about 190 hectares. This is our new laboratory. So now BRIN have a policy that we call it an open laboratory. So everybody can use this facilities in LIPI through this one, elsalipi.co.id. And this period of time, LIPI also have an open laboratory. This is our laboratory, and we have also a science technology park in Cibinong, and this is under construction, the biodiversity center, and this is in Yogyakarta for food center, food research center, and this is a genomic center. I think this year, this already ready this year. Okay, so we quickly look at the natural fibers in Indonesia. I think if you are not familiar, this is the plant natural fiber. We can divide it by non-wood fibers and wood fibers. And this is, I will give some example of these fibers. This one is natural fibers in Indonesia. We have a lot of, Prof. Basuki mentioned about the abaca. I think this one is abaca. And also from the oil palm. This is the straw fiber. You can get it from corn, rice, wheat, or sorghum. And bast fiber from the bark of this stem. We have a kenaf and rami. And leaf fiber, agave cisalana, and pineapple. We will got a very nice fibers. Also fruit fibers from oil palm or from coconut. And grass fiber, bamboo. We have about 180 species of bamboo from the small diameter to this big diameter. Also alang-alang and sugarcane. We also have a byproduct from rice and sugarcane, so rice straw and rice hulks and bagasse. This is, I think, the most abundant source of the cellulose from the oil palm. The area is about 15 million hectares. So now Indonesia is #1 in the world. This produce a fronds, trunk, shell, also empty fruit bunch. If we see the potential natural fibers in Indonesia, is mainly from this oil palm. If you look at the world fiber production, almost 80%, more than 80% is cotton leaves, and this one is jute and kenaf. This is the properties of natural fibers. Mainly they have these three, I think you are familiar with this one. Also, this is mechanical properties. If we compare the natural fibers and the synthetic fiber, natural fibers lower mechanical strength, but the density is much lower compared to synthetic fibers. Now we come to the first one, particle board from Sorghumba Gas. This is the picture of particle board and the application, mainly for furniture. And this is the production and consumption of particle board in in Indonesia and global. The production is, I think, this stack at 150,000 cubic meter. And this is only from 3 factories, I think, in Indonesia. And the consumption is higher. So we mainly import from China. And this is the production and consumption in the world, about 100 million. We use, because the particle board usually from wood, now we use this alternative bagasse from sorghum. This is a sorghum, mainly planted in Africa and Asia, 45 million hectares, and Indonesia about 25 hectares. And from sorghum, we can produce grain for food and bagasse. This is for bioethanol and for composite. And this is preparation of the sorghum particles. So we cut, and then using ring flaker, we got these particles. And then we use natural adhesive, citric acid and sucrose. This adhesive developed by Prof. Umemura from Kyoto University as an alternative for the synthetic adhesive. This is the preparation of the particle board. So we mix the particles with glue, dry, and mud form, and then hot pressing, and then we do testing. This is the first experiment on the sorghum particle board. We check the effect of citric acid content. Citric acid is quite a new adhesive for particle board. So we check the citric acid content, and we see we have two method here. Direct is we spray directly to the particles and then directly hot press, pre-dry it. We pre-dry the particles and then about 15 hours, 80 degrees C, and then we press. And the results show that the direct application is lower the properties compared to the pre-dry. And we can see here also see that citric acid content 20% is they have the highest mechanical strength. This is the internal bond strength, also the lowest thickness swelling. And we also do the cyclic test. So this is a kind of a very extreme treatment. So we boil and so on, and we can see here this is thickness change and this is weight change. We can see here that the direct method compared to pre-dried is better. This is the FTIR spectra. This is just to show that the ester linkage are from. And the second experiment, the effect of pressing temperature and time. This is the upper one, effect of pressing temperature, and this is lower one is the effect of the time, pressing time. And we can see here that at 200 degrees C, they have optimized the pressing temperature. You can see here, and also for the time, we can see that 10 minutes, the optimum pressing time. And this is the FTIR of this. This is the effect of pressing temperature, and this is effect of pressing time. Again, we see here that the formation of the ester linkage found here. And the experiment 3 about the sorghum particle board, we check we added sucrose in the citric acid. Why we add sucrose? Because when we just use citric acid only, the brittleness of this board is high brittleness. So we try to add sucrose to improve the bitterness properties. And we use this ratio of citric acid and sucrose from 0 to 90. And this is all sucrose. And this is the mechanical properties. We can see here that the G means the ratio of citric acid sucrose 10 to 90 is they have the highest properties. Also the internal bond strength. And here we can see this bitterness decreasing with increasing the sucrose. And we can get the best bitterness in this, the smallest bitterness in this G. This is we check this with FTIR spectra, and we can see here that similar to the previous work that we can form the ester linkages are formed here. And this we applied this particle board, the Sorghumba Gas citric acid, and the small furniture company to produce this kind of the board. And the second part of my talk is about the molding product from Sorghumba Gas. This is a kind of the molding product that we can find in the industry, for example, for automotive part or for furniture. And this car is a 100% nanocellulose vehicle. This developed by Professor Hiroyuki Yano from RISC Kyoto University. If you are interested, you can check it in this YouTube about this nanocellulose vehicle. And if we talk about the molding, we can have a sheet molding compound like this one. So we just put the sheet here and then mold, and we can get this shape. Also, we can use injection molding. So we can get this kind of shape using this injection molding. In our work, we use a simple hot press molding, something like this one. So we use a Sorghumba gas, make a particle, and then we mix with citric acid, and we have two types, powder and solution. And using this mold, we make a specimen from this hot press. And then we test the water resistant also from the bending test. This is the result. If we compare this powder type and solution type, and then a powder type is a bit better compared to solution type. And if we consider about the citric acid content, we can see here that 20% of citric acid get the highest properties also there in the modulus of elasticity. And this is the cyclic test. This is very severe test, and we boil, and we can see here that powder types is have a lower water resistance compared to the solution type. And again, we check with infrared spectra here that we can find this peak for the ester linkage here. So the last one is about the wild worm fibers, PLA composite. For the silk-based biomaterials, I think this is interesting. You can get it from spider or from worm. This is a Bombyx mori, but mainly Bombyx mori is for textile, so we can produce a lot of fiber from here, but this spider maybe it's difficult to get the fiber. So some researcher now try to make a synthetic spider fiber. This is the species, the silkworm, bombing mori, and the fibroin like this one, a bit oval like this one. And from the spider species, we can get more smooth and round, something like this one. And this is the processing. So with alkaline, we can get mud or cork, and also we can have this liquid solution. And this is the wildworm fiber we try to make for composite. The species Attacus atlas. The cocoon is more darker compared to Bombyx mori, and this is before degum and after degum. And the properties of this fiber, you can see here, the tensile strength is a bit lower compared to Bombyx mori. And when we degum the fiber, this strength is decreased. This is the composite that we make from the PLA and the Attacus atlas fiber. And we use the gum fiber and non-gum fiber. And this is the processing. And we use 5, 10, and 50% weight. And compare with Bombyx mori. And we can see here that Bombyx mori, the color is lighter compared to the Attacus atlas. And if we compare the strength, tensile strength and tensile modulus, pure PLA compared to this, we added the fiber, there's a slight increase, especially in the 5%. And we compare with Bombyx mori, almost similar mechanical strength. And also we check the thermal properties and here, and actually the melting temperature is quite similar to pure PLA. And this is the FTR spectra of the composite. This just to prove that using the fibers and PLA, this bonding already happened. This is application of the silk waste biomaterials, especially for textile and medical appliance, and also the composite. I think I would like to summarize our work. So we have a huge potential of natural fibers in Indonesia. I think this is we can cooperate to how to make a collaboration research on this one. And when we use, when we make a particle rock from Sorghumba gas using citric acid, we have to pre-dry it, and this is the condition: 20%, 200 degrees C, and 10 minutes. And addition of the sucrose improve the properties. And if we make a molding from Sorghumba gas molding, the powder application is can act as adhesive, and 20% the citric acid content. And for this PLA Attacus atlas fiber, addition of 5% degum fiber increase the mechanical properties. I think that's all. I would like to acknowledge the JICA, GST for the SATREPS program, also GSPS and RISC Kyoto University, and Research Center for Biomaterial Sprint. Thank you very much for your kind attention.
All right, thank you, Prof. Subiakto, for your interesting talk today. So we just realized how rich our country, in terms of natural fiber. You introduced to us not only the grass fiber, the wood fiber, even from sorghum, from coconut, and also palm oil and so on. Yeah, and yeah, it's really interesting to have a great setting from you regarding the development and applications, yeah, of natural polymer based biocomposite. In particular, from his presentations, we also can notice that we can do some modifications, yeah, by citric acid treatment or other materials in order to improve the properties, especially the mechanical properties and water resistant properties of the composite system to be meet and also applicable for commercial use. Yeah. Thank you, Prof. Subiakto, for your great setting this afternoon. And dear all participants, ladies and gentlemen, now finally we come to the fourth speaker for our seminar. And yeah, we have Bapak Dr. Muhammad Nasir. Here is his following CV. Yeah. Bapak Dr. Muhammad Nasir comes from Research Unit for Clean Technology, National Research and Innovation Agency in Bahasa. It stands for BRIN. Yeah, I guess this is also the same institution with Prof. Subiakto, but Prof. Subiakto in Serpong, Pak Nasir in Bandung, in BRIN Bandung. And here is his following educational background. He obtained the bachelor degree from Universitas Andalas and master degree from Institute Technology Bandung, both in the major of chemistry. And he obtained the PhD degree from Tokyo Institute of Technology, Japan, in the field of organic and polymer materials. And here is his following research interests. Yeah, he is currently working on nanostructure engineering. Yeah, development of electrospinning system, as well as the multifunctional nanofiber. Yeah, for preparing biocompatible nanofiber. Yeah, for certain applications such as advanced separations, water or wastewater separation, and even though for aerosol or nanoparticle separations. Currently, he in charge in certain project, yeah, in BRIN, yeah, regarding to the functionalizations of nanofiber for medical application project and development of nanofiber for lithium ion battery separations. Yeah, he has been published around 77 publications with the age in around 12. And still any other slide? All right. I guess without any further ado, Pak Nasir, place and time is yours.
Terima kasih Bu Fitri. Good afternoon, ladies and gentlemen. Selamat siang, Sensei Subiakto, Prof. Basuki, and Prof. Pakon. Okay, today I will talk about the challenge of the polymer nanocomposite for lithium ion battery separator. This work we conduct in Research Unit for Clean Technology, Research Center for Physics, and Research Center for Material and Metallurgy. This is outline of our presentation. First is motivation of our work, and the second is lithium ion battery and separator, and fourth is nano separator. In this case is based on silica and zirconia silicate. 5 is conclusion, and 6 is acknowledgement. Ladies and gentlemen, as we know, there is problem in our work now because our work full in pollution. As you know, we can see in this slide how our activity, human activity, for example, in domestic agriculture, industry, release the pollutant to our environment. So this is example of air pollution by transportation, and also we can see the smoke in the city caused by the industry. Based on the data from the United Nations, 7 million people death every year caused by air pollution. So this is a big problem to our human being in the world. So one way to reduce air pollution is by using clean energy. So the key is to use clean energy. How we can use the clean energy? So we should convert the current energy to new energy, to clean energy. For example, this is a world energy consumption. We can see here, year by year, the energy consumption is increased, and all of the source of the energy is release the pollutant to our environment, in water, in air, or in soil. You can see here, in 2020, around 35 million metric tons CO2 released to our environment. So one way we can use nanotechnology to reduce this effect of pollution. We can use energy storage. For example, the battery. We can develop the battery, in this case, lithium ion battery, by nanotechnology approach. We can see here the population of the electric car in the world. Day by day, population of electric vehicle increase, and also the electric bus. It means the trend to the future is we use the clean transportation. We use green transportation. It means in the future we need more lithium ion battery. So in conclusion, we can see here in the in vehicle, if we use the conventional vehicle, the CO2 gas and particulate matter will be released to our environment. But if we use the lithium ion battery electric vehicle, so we cannot release the pollutant to our environment. This is predicted population of the electric vehicle in the world. So the main player of lithium ion battery separator in the world is from the Japan and the Korea. Now China also the main player in the lithium ion battery separator. This is market of the lithium ion battery separator. In 2021, the market is around 5 billion USD, and predicted in 2026, the market is around 12 billion USD. This is very interesting in the perspective of business. So this is a basic concept of the lithium ion battery. Lithium ion battery, there is 3 main components: anode, separator, and cathode. This is mechanism, charge and discharge mechanism of lithium ion battery. You can see here the key of the when we want to develop the lithium ion battery, we should control the migration of lithium ion in cathode, in separator, or in anode. One approach is the people use nanomaterial approach, because by using nanomaterial, this is example. When we use the nanomaterial and the large material, so the transport of the lithium is very fast. And also when we use nano separator, the transport of lithium ion in the system also become faster. This is interesting research from the Kong et al. They developed the separator by using composite of the polyimide and silica. they developed the thermal stable of the separator. So what is nanofiber? Because they developed based on the nanofiber composite. Nanofiber is fiber with diameter less than 1,000 nanometer or 100 nanometer. You can see here this is morphology of the nanofiber. We measure by using scanning electron microscopy, and this is cross section of the nanofiber. This is basic property of the separator, commercial separator. Most of the material is from polyethylene and polypropylene, and the property of thickness is very important, and also the permeability or Gardy is an ionic resistivity and porosity. And the one important is melt temperature of the material, the polymer material. This is a detailed requirement for lithium ion battery. So when we want to design the separator, we should consider the thickness, structure, integrity, thermal stability, and mechanical property. This is current status of research of lithium ion battery and separator in the world. We search in American Chemical Society. You can see here there is huge publication about the lithium ion battery, around 20,000 articles and 15,000 articles about the lithium ion battery separator. So if we want to develop the nano separator, so we should enhance the safety of the battery, and also how to make long cycle life of battery, high capacity and high density of battery, and also how to make low price of the separator. And another one is we should consider the eco-friendly material when we use to separator. This is a famous tragedy of the how affect lithium ion battery if the shock occur in this battery. You can see here the Boeing, Boeing Dreamliner cannot be used because the accident of lithium ion battery in this system. Okay, we continue to produce the separator of lithium ion battery. There is two types, the current process to produce the separator. You can see here, there is a conventional process and nano process. In current separator, they use a conventional process. They use melted polymer by using polymer extrusion to make a thin film, and then they do the thin film stretching to make pore in the thin film, and then they use as a separator. The porosity is around 40%. By using nano process, we can use a polymer solution or melt polymer. The process, most of people use the electrospinning process. By electrospinning process, we can make a thin film with control for size and porosity. In this case, most of nano separator, the porosity is between 50 to 80%. Okay, this is a process or method to make a separator by electrospinning process. There is electrospinning parameter. First is solution parameter, for example, the concentration of polymer, surface tension of polymer, and conductivity of polymer. And second is the electrospinning parameter, for example, apply voltage, feed rate, nozzle to collector distance, and humidity. This is step to make a separator by using electrospinning process, because we use high voltage. The first is charging of polymer solution, concept formation, strike jet, bending instability, and solidification of polymer. This is example of the electrospinning machine we developed to make a separator. Okay, now we try to make a separator based on the silica and co-PVDF nanofiber. As we know, silica is a very, we can control the thermal stability of the composite by adding the silica. And also we use the co-PVDF polymer because this is a good physical and chemical stability. And we use the MSA solvent. And then we produce the separator by using electrospinning process. This is the result of our research. This is separator based on the silica co-PVDF nanofiber composite. You can see this is pristine of co-PVDF polymer. By adding the silica, the diameter of the fiber is decreased. From this result, we can see the optimum condition of composition formulation is 0.5% of silica. We can make a very thin and homogeneous nanofiber. We confirm the functional group of the composite. We can see, we can observe by infrared spectroscopy. We can see here the silica in silanol group of the silica. And also we can see here effect of silica on the crystal structure or crystal phase of the PVDF. You can see here the beta phase content decreased by increasing the silica content. And then we confirm by XRD. You can see here, this peak to theta peak is related to beta phase, and this related to alpha phase. And then we measure the crystality. So the crystality around pristine co-PVDF is around 54%. By increasing by adding the nanosilica, the crystality is decreased. And the important point is the thermal property of the silica co-PVDF nanofiber composite. We measure in the nitrogen and oxygen atmosphere. You can see here when we silica will give effect to the thermal stability of the composite. You can see here the degradation process of the PVDF, co-PVDF is around 420. But when we use, when we add the composite, the degradation process will temperature increase. And then we develop, based on this, we develop the zirconia silicate co-PVDF nanofiber. We use nano zirconia, co-PVDF, and DMSA solvent. This is a basic characteristic of the material we use. This is morphology of zirconia silicate. We measure the particle size. The particle size is around 300 nanometer. Okay, this is morphology of separator. You can see here, this is pristine co-PVDF separator. And when we add the zirconia silicate, the diameter of the fiber is decreased. And also we get the optimum composition is in the zirconia 5%. And then we measure the distribution of nanoparticle in the nanofiber composite by using EDS, same EDS. We can see here, this is zirconia, this is silica. And this is composition of the nanofiber composite. And then same, we confirm the structure of the polymer by using infrared spectroscopy. We can see here silica, oxygen, zirconia here. And also we observe the crystal phase of the PVDF in this composite. And then we confirm again by using the XRD. We can see it's very clear. You can see here the crystal phase of the co-PVDF, alpha and beta, and this is the 2 theta peak of the zirconia silicate. It's very clear. And then we study the important point of why we use the zirconia silicate. You can see here we do experiment in nitrogen and under oxygen atmosphere. We can see here when we use zirconia silicate, the degradation rate of the decomposition will decrease. So it's very important if we use lithium ion battery in the high temperature. This is physical. Yeah, we do the Silicate Test. You can see here. This is pristine nanofiber, and this is after heat treatment. And this is a surface property of the nano separator. You can see here when the increase of the zirconia silicate, so the water contact angle is increased. So this character show this separator has a hydrophobic character. And then we try to measure the performance of the separator by using by coin cell test. You can see here this is pristine co-PVDF separator. This is zirconia co-PVDF separator with different zirconia content. This is a cell guard separator. You can see here, in general, the performance of nano separator in terms of the capacity is higher than the conventional separator from cell guard. You can see here, this is capacity is higher than the cell guard. So in the optimum, we get optimum composition is around 5%. We can get capacity around 174 milliampere hour per gram. So, and also we observe how the property of relationship between charge discharge capacity and voltage. You can see here, this is this chart. You can see here, the composition of the composite influence the property and performance of the battery. The best one is in composite 5%. And also we observe the IV curve of the lithium in battery. This is cell guard conventional battery. This is the nano separator. And the important point is the durability and cycle performance of the battery. So we do the C-rate test. We use from the low C-rate to the high C-rate. So you can see here, this is very stable. And the important point is after we use the high C-rate, and then we go to the low C-rate, the performance is still same. It means the stability of the separator is very good. And then we study the morphology of the separator after we use. You can see here this cell guard separator. This is new separator. This after we use. This is new separator, and this after use. And in the case of the composite, you can see here this new separator. This is after we use. We can see there is a particulate in the surface of the separator. I think we think it will influence the porosity and pore size of the separator. and then we observe the composition of the used separator. The result is here. And then conclusion and future outlook. First is nanoseparator based on the polymer nanofiber composite have been developed and tested. Second, nanoseparator based on nanofiber composite has better performance than the current conventional separator. So there is still room to develop new nanofiber composite nanoseparator by adjusting composition of polymer nanocomposite and doing post-treatment of nanoseparator. 4. It is required to solve the issue, the pore blocking phenomena in nanoseparator. We acknowledge to our government for financial support through LPDP project, and also to our team in environmental nanotechnology research group, and also special thanks to our student and research assistant to do this experiment, and also special thanks to our research collaborator in Lithium Ion Battery Consortium, Mr. Ahmad Subhan, Dr. Iva, Dr. Mona, and Dr. Bambang. Thank you. That's all of my presentation.
Okay, thank you very much, Pak Nasir, for your excellent talk today. Pak Nasir, share with us about the development of nanomaterial composites, for preparations of separator, that can be applied in the lithium-ion battery applications. From his presentations, we can notice that the employment of nanofibers as the material for separator must be meet to the several requirements, in terms of thickness, structural integrity, as well as thermal and mechanical stability. And in his presentation also, he shared with us some report on the preparations of the nanofiber composite as the separator, by using electrospinning method. In this case, Pak Nasir employ silica as well as zirconia silica, combined with CPPD, PPF polymers, and we can see in detail about the great performance that can be demonstrated by this composite system, especially in terms of its performance as the nano separator for lithium-ion battery applications. So again, thank you to all speakers who have delivered the presentation today greatly. And dear all participants, ladies and gentlemen, finally we come to the last sessions in our seminar. It is the Q&A sessions, and as we can see here from the chat room, there are quite a lot of questions come from the participants, and then let me start one by one. For the easiest one, maybe we can start from the bottom part since it's already scroll up. Firstly, there is the questions for Prof. Basuki. Yes. From Tri Anissa Rahmawati. Maybe I can help you to read the question, Prof. To Prof. Basuki, I use ImageG. ImageG to calculate is a kind of software, I guess, to calculate the contact angle and use drop analysis feature. So the drop analysis that I use is LB EDSA, not drop snake. So actually, I still feel confused about the specific functions, both of them in calculating the contact angle. So could you please kindly give the explanations? Silakan.
Well, can I make comment? Just comment, maybe. Fitri. So actually, we've done about the contact angle. Actually, we just measure the surface energy, because there is a relation between the surface energy and the contact angle. There is a very famous equation. I don't remember the formula, but there is a direct relation the surface energy with the contact angle. So actually we just measure the contact angle, and then we can get the surface energy. So on the surface energy we can predict the compatibility. If the surface energy between two surfaces almost similar, and we can predict the compatibility is better. That's the thing. So I don't use any very advanced calculation or something like that. Just direct formula. Yeah.
I see. All right. So, Ibu or Ms. Trianisa, hopefully it answers your questions. If you still have any additional question, you can continue, yeah, by maybe raising your hand or write down again the additional question in the chat box. And next we move to the second question from Adam Nugraha to Prof. Prakon. Dear Prof. Prakon, what is the prospect of MNP for MNP materials, that you just developed for COVID-19 treatment? And is it possible to heal the broken tissue due to the COVID-19 using the enhanced MNP? Yeah, please, Prof.
Okay, that is very good questions. To address that, I would say the function of magnetic nanoparticles in drug delivery is number one, maybe as targeting or carrier. So if we incorporate magnetic nanoparticles into drug encapsulated materials, right? We can use external magnetic field to carry the drug, right? So we can carry the materials, right? Go to a specific location. That is one of the function, right? Number two can be during the carry of the drug, right? We also can monitor the materials, right? Using what we call magnetic contrasting, right? So we can use machine like MRI to detect the magnetic nanoparticles, and we know exactly where they are. Number three can be heating them, right? So as I already mentioned, we can use inductive heating machine to heat magnetic nanoparticle, right, to higher temperature, and this therefore can trigger some other mechanism, right? So from this, the last one may be the ability to concentrate the material, right? So if we distribute material that contain magnetic nanoparticle into large volume, we can use magnetic field, right, to pull them, right, and make them concentrate to a smaller volume. By doing this, we can increase the sensitivity of our measurement or our detection, for example. Okay. So to answer this question, I would say magnetic nanoparticle may not be able to heal, right, the damaged tissue or something like that. However, if we incorporate magnetic nanoparticles into material that have drug with a specific treatment, that is possible. And for COVID-19, I would say we may not need the function of magnetic nanoparticles, right? But for detection, maybe if we want to develop a test kit to detect the virus that caused COVID-19, if the sample has very low concentration, right, we can use detecting species attached on magnetic nanoparticles and concentrate that, and then can detect it with higher accuracy. That is possible.
Yeah.
I hope that answer your questions.
Yeah, very difficult question. Pak Adam or Mr. Adam, if you still have any further questions regarding to your previous question to Propakon, if you can open your microphone, also you can directly deliver your question in advance. So during we waiting for other question, we can move to the third question. It comes from Dwi Febriantini, Ibu Dwi Febriantini. The question to Prof. Subiakto. So dear Prof. Subiakto, does the source of natural fibers determine what type of the product can be made? And how is the stability or quality of natural product fibers compared to the wood product?
Okay, thank you very much for the question. So the source of natural fiber, actually, if we depend on the product, if we use it for example, for molding product, and we crush the fiber into the very small particles. So I think in this type of product, I think the chemical components of the natural fiber maybe has influence on these properties. But for other product, for example, for particle board, for example, I think still wood is still better compared to natural product. So we cannot find now in the world that particle board made from natural fibers, mainly made from wood. But other products, for example, for molding product, I think one of the automotive company in Indonesia already use a molding product for their interior part of this their cars. And I saw one factory in East Java in Pasuruan that's produced that kind of product. So the stability, I think the stability is depend on the matrix used, and when we use for example, citric acid, and then we will have a high dimensional stability, but a little bit low the brittleness. So I think for the compared to wood, I think depend on this matrix, I think. But the natural fiber, usually they have the homogeneity of the natural fiber is not quite good. Depend on this where they planted or the age when they harvest and something like that. So in this point of view, the wood is, I think, still better.
Yeah.
But I think we have to search these natural fibers for other value-added products because of the wood and the forest already decreased.
Already declined, yeah, bro.
I think I hope this answered the question. Thank you.
Yeah, it means the wood product still superior, compared to other natural fiber, and in terms of stability properties, it really depend on some parameters, when it's planted, when it's harvested, and so on. All right, Dwi, Miss Dwi, hopefully the answer from Prof. Subiakto can replay your questions. And if you still have any additional question, you can raise your hand, or even though you write down again the additional question. And next, another question from Department Pendidikan Kimia. Dear Prof. Pakon, I'm curious about the performance of antiscalant that developed in your lab compared to the commercial antiscalant. Maybe how it comparable, maybe, Prof. If you have any data.
Okay. Yes, actually, we have the test data on performance of the developed materials. They are comparable and even better than some of the commercial anti-scalant that are available in the market. And now, so we are developing or we are scaling up the production process, right, for producing this in larger scale, right, for commercial use. That is on the Kaitosan Polyimphalite, right? So which will be much better than the commercial anti-scalant, because this will be much friendly to the environment and also come from bio-based materials. For the other system that we incorporate magnetic nanoparticles, those are still in practical use. If we want to apply that, right, for reusable materials, we need the magnetic collecting system, right, to be incorporated with that materials. There are some aspect that we need to further develop in order for them to become commercially available.
Yeah.
So, but for the Kaitosan system, they are promising.
How about the cost production?
The production cost depends mainly on the price of Kaitosan raw material. Right? The production cost is not much at all. And also the chemical that we use in the production is not expensive. This has very high potential, promising.
Yeah. Since it's how to say, environmentally friendly, yeah, much more.
Right.
Yeah. All right. Hopefully it answers your questions. And then next we move to another question. The question to Prof. Basuki. Prof, regarding to antibacterial activity, what was actually the mechanism occur between the polymer or hydrogel precursor with bacteria colony, and which component predominantly determined as antibacterial agent in your composite system? Please, Prof. Basuki.
Well, this is a very hard question for me because this is out of my area actually about the microbiology. Well, actually we have done already. We have done actually only immobilization of the bioactive extract. So after immobilization, some component. Yeah, because they actually have many different components, and some components maybe can be trapped further and really slower. Yeah, and of course, when we compare to the original extract, yeah, after immobilization, there is a possibility a different mechanism of antibacterial. Yeah, but the main thing is. When we immobilize the extract, we can have a slow release of the extract into the substrate, for example. Yeah. So maybe of course we have to study further about how's the effect, because they have different components released in a different speed. So maybe the mechanism will be different. Yeah. So actually, I can answer this question so much. Sorry about that. So maybe you can discuss later.
Yeah. All right. Maybe there are some possibilities, yeah, for the mechanism that possibly.
Yeah, it should be different mechanism because different components.
Yeah. All right. Prof. Basuki, very welcome to have further discussion with you after this seminar for this matter. And then let's move to the next questions to Prof. Parker. The question from Amelinda. Thank you, Prof. Parker, for your great presentation. I would like to ask about the smart gating, or the last topic, yeah, that you delivered. How do you optimize the smart gating, especially for drug delivery in cancer? I'm curious how the smart gating, especially in cancer drug applications, can exactly on or off on the cell and affected by the cancer, while the environmental condition in the human could be variable. So please, Prof.
Okay, very nice question. Yes. So when this type of materials is applied into the biomedical application inside our body, especially for cancer drug delivery here. So the stimulus that we use in order to trigger the release need to be from the remote site, right, outside of the body. So that can be done by various ways, right? Applying ultra sonication, for example. This also can heat up, right, local environment in our body, right? But for the specific example in our work, when we incorporate magnetic nanoparticle here with the particle, for example, that can be precisely heat up very fast, right? So if we incorporate the magnetic nanoparticle and we use induction heating, right? So if you know, right, induction heating is similar to electric pot that you use in your kitchen, right? Only contact, and it will get hot, right? So we can do that as well. Right? So we can use the electromagnetic wave, right, and send into specific location that we have the drug already, and then so by using that we can heat up the particle very efficiently and very fast, and then the drug get released from the particle, right? So that is only one example, but we can do some other way as well, right? There are some, various type of technology available, right, to trigger, right, the release of various type of materials.
All right. Still, we have some questions. Before we continue the questions in the chat box, I would like to move to the question in YouTube, because we also stream live this seminar in our YouTube channel. So the question was to Pak Nasir. Yeah, I'm curious about how you synthesize the nano silica and zirconia silica. Yeah, since from some images, maybe from ACM images, it can be blend very well with the CPVDF nanofiber. And the next question, why you choose silica and zirconia silica, yeah, for the composite system? Please, Pak Nasir.
Okay, thank you very much for the question. We synthesize the zirconia silicate in our partner in industry. So this is, I can tell the formula how, because we have a collaboration with industry in this project. Why we choose the silica, nano silica? Because the nano silica we can improve the thermal stability. And why we choose the zirconia silicate? Because by using zirconia silicate, we can improve the thermal stability, mechanical property, and the fire resistance of the separator. Okay.
Yeah, my additional question regarding to that question, Pak Nasir, is there any other metal oxide that also potential to be employed in your composite system?
Yes, we develop some metal oxide composite in our system, but in this case we try to improve the thermal property and mechanical property and fire retardant property. But in another composite, metal oxide composite, we also try to improve the electrical conductivity of the system.
All right, thank you, Pak Nasir. So for the participant in YouTube, yeah, hopefully the answer can meet to your questions. And then let we back to the chat box. Still some question here available. So the next question is to Prof. Subiakto from Department of Chemistry. Prof. Subiakto, besides the mechanical and water resistant properties, is there any other parameters need to take into account on preparations of your composite product materials?
Thank you very much for the question. When we talk about the particle board, there are some standard, for example, Japanese industrial standard for particle board. And mainly they mention about the mechanical test and also the water resistant test. But I think depend on the application of the product. For example, for furniture, there's also a test for termite resistant, also for fire resistant of the product. So I think many parameters that we can also test it for the particle board product. Also, I think the important thing is about the formaldehyde emission, because usually particle board or plywood use formaldehyde-based adhesive. So we have to consider about the emission that are toxic for the human health. And for molding product, for example, for the interior or exterior of the car, I think the impact strength also important. Also for the interior, maybe the smell of the, sometimes the natural fiber smell good for the interior, sometimes it smell not good. So I think the impact strength or fire test and fire resistant, or also the brittleness is also among the parameters that we need to test. Thank you.
All right. Thank you for the answer, Prof. Subiakto. And there is another questions in the chat box. Ms. Dwi Febriantini, are you there? Are you here? I'm not sure this question is quite clear. So dear, to Prof. Basuki, the question. Dear Prof. Basuki, does the molecular weight PS of polymer influence their function? Miss Dwi, are you here? Are you still here? So could you please open your microphone? Maybe you can clarify your questions just in case, yeah. Or
yes, Miss.
Oh yeah, please, kindly, please.
That's my question is the molecular weight of the biopolymer is influence the function of the cell. Thank you.
Yeah. Okay.
Please, Prof. Basuki.
Okay. Thank you very much, Ms. Dwi Febriantini. Yeah. So actually, we produce many hydrogels and biopolymers as well. Yeah. In the case of hydrogels, because hydrogel is a cross-link biopolymer. So the higher the cross-link density, and then the hydrogels become harder. And of course, if the cross-linking is very heavy, and then it become the absorption of water maybe become smaller. Yeah. This is regarding the hydrogels. Yeah. So actually, we need the hydrogels. The optimum hydrogel is if we can get about maybe 500, more than 500% absorption of water of the hydrogel. So we don't need a very high cross-link density of the hydrogels. But in the case of when we're talking about the addition promoters in the in our first results, this is we have actually addition promoter, high molecular weight and low molecular weight of addition promoters. So addition promoter actually just like coating, pre-coating on the surface of the substrates, which one substrate which is we going to coat or something. Yeah. So if the high molecular weight of the adhesion promoter is compared to the low molecular weight, we mentioned in our result that the high molecular weight promote better mechanical strength. But the low molecular weight promote less or lower mechanical strength. This is actually very tricky, because how the adhesion promoter actually function on the surface depend on of course, on the molecular weight as well. Because the longer the molecular weight, maybe the adhesion promoter can diffuse on the surface of the polymer surface. But when the lower molecular weight, maybe it can migrate faster. So we can maybe will be more compatible to low molecular weight. But everything is depend on the type of the polymers. So it depends on the function actually. So as a conclusion, that in the case of hydrogels, the higher molecular weight or the higher cross-link density, maybe they can produce slower release of the extract in the hydrogel, but they only absorb less extract in the hydrogel.
All right.
I think that's all, maybe.
All right. Thank you, Prof. Basuki. Miss Dwi, is it answer your question?
Not
Yes,
really,
thank you,
maybe.
Bu dan Pak.
All right. Thank you, Ibu Dwi, for some questions you just delivered. And we still have 2 questions in YATAP. The question to Prof. Pakor. Dear Prof. Pakor, could you please kindly share the photocatalytic activity of your MCIN, titanium oxide catalyzed performance in case of dye degradations? Please, Prof. Pakor.
Okay. So, so the question was to
maybe regarding to the photocatalytic activity of your MCIN titanium oxide composite system on dyes or organic compound degradations.
Right. We developed the composite system, right, for 2 functions. Right, the MCIN itself is for absorption of various compounds, and we test that with some model compound, right, fluorescent dyes or various type of indicator, and it worked very well. And also we test this on different type of antibiotic drug as well, right? Which are pollutant in water. So to absorb that alone, right, may not be quite convenient, right? Because after absorbed, we may need further process to remove them, right? That's why we incorporate photocatalyst, right, with the materials. So the titanium dioxide nanoparticles, right, help degrading the organic species that are absorbed onto the MCIN structure, right? This can work well with almost every type of organic compound. Yes. And we have conduct that work is undergoing as well. We test the system with various type of pollutant.
It's a kind of a smart hybrid system, that can, how to say, synergic each other,
multifunction, like synergistic effect.
Very nice. Very nice, Prof. Hopefully the answer satisfied you for the one who delivered the questions in YATAP. And
there is I'm sorry, there is one direct message to me
Oh
from
yeah.
Dr. Trianisa
Oh please,
Ramawati. Right?
Yeah.
I think she said she have some question about Raman spectroscopy from last time, but she did not have a chance to ask because she has maybe lecture every Friday, something like that, and asked me if she can directly contact me. Yes, you're welcome to email me or I think my email is already announced, right?
Yeah.
And then we can discuss further if you like. And this also apply to other audience as well. If you would like to discuss further detail, you can also contact me. Thank you.
Thank you, Prof. Makwan, for your great availability. Just in case it's really, how to say, highly wishes by the participant, maybe on our next FGD, we can specially open for the meeting, especially to discuss about Raman spectroscopy, maybe, Prof. Makwan.
Sure, yes.
If you are available, and I will prepare the notifications as well as the invitations, to participants or audience who would like to learn more about the Raman spectroscopy from Prof. Makwan. Last seminar, it was so attractive and many questions come, even we have not enough time to reply. All right, thank you, Prof. And last question here in Yata come to Prof. I guess this is to Prof. Basuki.
Yes.
Dear Prof. Basuki, the utilizations of natural cellulose is really interesting. Based on the treatment that you have been conducted, how about the economical aspect of the polymer produced from banana and durian peel?
Well, can you repeat the question, please? I'm not very clear for me. It's about apakah banana stem.
Regarding to your research work, how about the economical aspect of the synthesized polymer composite that produced from banana and durian peel? Do you have any studies regarding to the economical aspect?
Well, yeah, still far way to go because we just only doing a basic things. Well, just the beginning, but we mentioned that we get a lot of natural resources available here. Well, in South Asia, in Thailand as well, actually, we can utilize it, and especially the nanocellulose. You can have, Prof. Makwan mentioned that the nanoparticle, they have a very eccentric use for even for cosmetics, whatever, but I think in the case of what we call it specialty polymers, specialty polymer, biopolymer, medical polymers will be have more prospect this one, because the specialty polymer is more expensive, about the cosmetics, everything is very expensive. And you talk about cosmetic, the lady know that everything is very expensive. So we go to cosmetics, food, drugs, and medicine. Maybe the economical aspect is very, very, very bright. Okay, I think there's a little comment from me. Thank you very much.
It could be a new idea for your research team, to study about the economical aspect in the future. All right. More than 30 minutes, we have Q&A sessions. Thank you so much for your great questions, and also thank you so much to all invited speakers who already provided.
Okay, everybody welcome.
Before
pleasure for us.
Before we close the sessions, still I would like to hear from the participant just for the quick question or comment, if you still have any questions. Any? Oh I guess everyone's already tired. Time flies so fast. Well, almost 3 hours more. We've been in this seminar. So before we close this last seminar in our World Class Professor program for this year, I would like to give the opportunity to each invited speaker here to deliver your closing statement. So we can start maybe from Prof. Pakon, and then continue by Prof. Basuki, and then Prof.
Thank you.
Sugiarto, and then finally by Pak Nasir. Please, Prof. Pakon.
So I would like to thank all the distinguished invited speaker who give talk today, and also this which make this lecture very informative, and also we have a very fruitful discussion among us. And as this is the last lecture of the series, right, I also would like to thank Professor Fitri for inviting me to participate in this program again for the second time, continue from last year. And this is a very, very good program, and that provide excellent opportunity, right, to share our research work, and also to conduct collaborative work together, and have a very good output and from our research together. That is an excellent opportunity that we can do together. And also the lecture, right, from in this series, from lecture 1 until today, lecture 4, and also with presentation from other distinguished speakers who join for all of the seminar. I hope that this can be a good point that we can start, right, to realize mutual interest with each other, and hope that this can also bring up some initiative or collaborative work in the future, right? And I also grateful to the supporter, right, from the Ministry of Education and Culture,
yes,
of Indonesia, and also Department of Chemistry, UPI University, and especially for Professor Fitri for organizing this event. So thank you very much. Oh, but last but not least, I thank all the audience who attend, right, our lecture here from lecture 1 until today. Thank you very much for your kind attention. Thank you, and hope that this program will continue in the future and bring up some good work. Thanks.
Yeah, hopefully. Thank you, Prof. Pakon, for really great concluding remarks. So hopefully next year COVID is over, then we can visit each other. Because the initial scheme is I can visit your lab, and then you also can visit Bandung. Yeah,
right,
yeah, we really do hope so. Yeah, thank you, Prof. Pakon, for your great and continued support. And next, Prof. Basuki, please.
Okay, well, yes. Actually, I'm the honor to join here in this discussion. So actually, I don't have much to share, but I got a lot from everybody, from the speaker, from Prof. Pakon, from Prof. Sugiarto, from Dr. Nasir, yeah, and all from the participants. Actually, the participant is very interactive, and they are very creative. So that's why I can't answer all the questions properly, because actually we have so many problems, especially in the natural resources here, because we have not yet utilized it optimally, our natural resources. Hopefully from this meeting, from this discussion, we can open up our discussion further and collaboration, as Prof. Pakon mentioned, in research. Especially in the Asian, we are just like a one nation in the Asian countries.
Right.
I feel home. I went to if I went to Thailand, I feel home. Everything I have, everything, the food was exotic and everything.
Please.
Okay, So hopefully, as Dr. Video wish, we can have maybe we can meet each other next time. Yeah.
Yeah.
In real meeting, not
Sure,
only
sure, bro.
online
Mhm.
meeting like this.
Yes.
Yes.
So the collaboration may be more realistic. Yeah.
Yeah.
Okay. Thank you very
Hopefully.
much, everybody, and especially to organizer. Yeah. Dr. Fitri is very, she's a very charming lady, very great, very, you know, progressive lady and very productive. Yeah. Hopefully, she will be a great professor soon.
Thank you, Prof. Basuki. Thank you.
Thank you very
Thank you
much.
so much for your great support. And
Yeah.
as Prof. Pakon highlight, hopefully after this meeting, soon after we can make more connections. Yeah, not only the connection between me, myself, and Prof. Pakon, but later on maybe tripartite, propartite, and so on. Yeah, become wider,
Yes.
and yeah, we can put our innovations and contribution to society, yeah, through research. All right, thank you again, Prof. Basuki. And next, Prof. Subiakto, Dozo Sensei.
Thank you very much, Bu Fitri. Thank you for inviting me in this seminar. I think also thank you for the other invited speaker, Prof. Pakon and Prof. Basuki, and also Pak Nasir. Yeah. This is more, I think more chemists go together. So I feel like an alien come to this seminar. I'm from the other side of the composite, but I am very happy to become this speaker of this seminar. Hopefully that we will have a future collaboration, especially for Prof. Pakon, also Prof. Basuki and Pak Nasir and other participants. So we looking forward because in BRIN now we have 4 institution become one now. So
Larger, yeah,
larger. This is a very large organization, and we have a policy of open laboratory. So our laboratory can be used for anybody. Yeah. Of course, there is some
Thank
rules.
you, Prof. Biakto. Yeah.
So we invite all of the participants here to make a collaboration with BRIN.
Yeah.
And hopefully, I agree with Prof. Basuki that the natural fibers, we need to explore more in this field. Yeah.
Right.
Many chance to be searched in this natural fiber.
Yeah.
I think thank you very much also for the all the audience. Thank you for the question, and thank you again for Bu Fitri. Yeah, thank you.
Yeah, Anthony, arigatou gozaimashita, Sensei. Thank you very much. Yeah, we really enjoy, even though you deliver in the agriculture side, in other side than chemistry, but we enjoy. We finally knows, yeah, the real application, why it needs to be modified and so on.
Yes.
Thank you, Prof. Subiakto, for your great lecture. And the last, Pak Nasir, please. Still mute, Pak Nasir?
Still mute.
All right.
Okay, thank you very much, Ibu Dr. Fitri. I think this is great work from the Ibu Dr. Fitri and team from UP, Department of Chemistry UP, to arrange a conference between ASEAN country, Thailand and Indonesia. I think this is great work, and as said by Professor Pakon, Professor Basuki, and Subiakto Sensei, I think the next is the real work, how we make real collaboration in the research. I think this our next lesson, I think.
Yeah.
Thank you very much.
Thank you, Pak Nasir. Thank you again to all distinguished speakers. It's more than happy for me on behalf of the committee of this program, and also on behalf of the Department of Chemistry here in the final sessions of this seminar, I would like to deliver our sincere gratitude for your excellent and wonderful contribution on our seminar. Bu Amel, could you please kindly share the slide for the e-certificate? Yeah, it's more than word actually. We don't have any better word to deliver our sincere gratitude for your wonderful and excellent contributions in our seminar series. Thank you
Thank
again,
you very much.
Popcorn. Yeah,
Thank you very much.
we really happy to have you for almost 2 years. Yeah, so hopefully maybe next year we can strengthen and continue our fruitful collaborations. And also to Prof. Basuki, even though we never meet people in the real time, but yeah, this is the first time we have a chance to meet each other virtually. Again, thank you very much for your excellent talk in our seminar or podcast professor program. Thank you, Prof. Basuki. And to Prof. Subiakto, Sensei, domo arigatou gozaimashita.
Thank you very much.
Really happy to know Prof. Subiakto. Hopefully in the future you still have great availability to have discussion with me, Prof. Thank you for your wonderful talk in our seminar.
Okay, thank you.
And yeah, the last but not the least, here is the e-certificate for Dr. Muhammad Nasir, Pak Nasir. This is also my, loyal collaborators. I have been collaborating with Pak Nasir and his team in LIPI Bandung for almost 3 years, and hopefully later on we can extend to USU, to Serpong, and to other places for continuing our research work. Thank you, Pak Nasir, and again, just reminder to all participants who would like to earn your e-certificate, please kindly fulfill the attendance links soon after you complete your information. In this form, we will send the e-certificate to your email address or any contact that you provided to the committee. All right. And finally, dear all distinguished speaker and all beloved speaker, we come to the end of this session. And yeah, time flies so fast. I still remember on the last of August, we started this program, and then finally we almost come to the final touch of this program. And tomorrow I will have the monitoring and evaluation session with the ministry, and this program will be reported to the ministry by tomorrow. And the photograph of Prof. Basuki, Prof. Subiakto, Prof. Korn, of course, and Pak Nasir will be displayed in our poster. Again, thank you so much.
Okay, thank you.
All invited speakers,
everybody.
Stay happy and wish you all a great weekend, and see you again in other
Thank you.
events.
Thank you.
Thank you. Selamat sore.
Bye.
Thank you so much.
Popcorn. Ya. Thank you,
Sehat-sehat,
Biakto.
Prof. Sensei, domo arigato.
Nasir. Ya.
Hai. Thank you so much.
Okay.
Thank you, Prof. Basuki. Thank you, Pak
Okay,
Nasir.
thank you, Bu.
Ya,
Fitri,
sehat
ya.
selalu, Prof. Insya Allah ketemu lagi.
Insya Allah.